process in the semiconductor, the VLSI, can be distinguished into two processes. One is the predeposition, and the other one is the drive-in. Okay, the predeposition is just a we want to put a certain amount of charges of the dopant during the predeposition process. And the drive-in, we just make junctions to make it diffuse into the substrate. Okay. In the diffusion furnace, what you do is you maintain like 1000 degrees centigrade. The temperature is around 1000 degrees centigrade. And then you place your wafer, silicon wafer here, and then you use a mask with a silicon oxide and a pattern in this fashion so that only this part of the silicon is going to be contaminated, you should say, with the dopant atoms. And then you put the dopant as a gas, like B2H6 for the borons, and pH3 for the phosphorus, and so forth. Okay? This is basically what happens in the diffusion process in VLSI. And then during the predeposition, you just use the source and then make it react. The surface of the silicon is going to be reacted with the dopant atoms. And after that, you load a certain amount of dopant into the surface of the silicon. Then you cut down this source gas, and then you just use the elevated temperature to make it diffuse into the silicon from the top. Okay, that is a drive-in. Excuse me. That is a drive-in process. So we can distinguish two processes. And diffusion happens, as you see, we have two types of diffusion process: interstitial diffusion and substitutional diffusion. Okay, interstitial diffusion and the substitutional diffusion in the diffusion process. Interstitial diffusion is just the dopant atoms that's going to move around in between the host atoms, right? But in the substitutional diffusion, you have to incorporate with the vacancies and the dopant atoms. You have to have a coupling action of these two to make a substitutional diffusion. Okay, so substitutional diffusion is always slower than the interstitial diffusion. Interstitial diffusion is very much, you can see the diffusion coefficient of interstitial is very much higher than the substitutional diffusion. And most of the impurities in the semiconductors, like ions and lithium and copper and other heavy metals, all those like silver and gold and things like that, there's a typical dopant impurities in the semiconductor processes. All those impurities are diffused with interstitial diffusion. Ironically, and so this is very fast. The contamination speed is very fast, so we have to be very careful about that. But the dopant atoms like phosphorus and boron and arsenic and antimony, things like this, all those dopant atoms are moving in the substitutional diffusion. So they are relatively very slow than compared to the impurities diffusion. So that means doping is difficult, but the contamination is very easy in the VLSI process. Okay? And diffusion coefficient itself is kind of an Arrhenius type. Thermally activated process, so that the diffusion coefficient can be written as a Arrhenius type plot like this. So if you plot the log D over 1 over T, then you have a straight line, and here you have an intersection which is D naught. That is related to the vibration frequencies of the atoms at a certain temperature. And then that is E star over K. That is related to the activation energy or diffusion mechanisms of the dopant atoms. Okay, that is a typical things related to the diffusion. Okay, and in the text we have diffusion. Okay. Let's see. There is interstitial, and then diffusion theories. We have a fixed first law and fixed second law. Okay, fixed first law is this, and then fixed second law. You see, we can have, if we can assume that no electric field effects and diffusion coefficient itself is not that sensitive to the concentration of dopant, then we have this simplified the partial differential equations to get the dopant profile inside the silicon. Okay, and then here is the diffusion coefficients, and see the most of the important dopant atoms are diffused along with the substitutional diffusion, and that diffusion coefficient has a Arrhenius plot, and the constant related with them has been tabulated in this table. And this is the typical diffusion coefficient of the impurities. Lithium, iron, copper, gold, things like that. And you can see the y-axis here is very much different from the y-axis of the substitutional diffusion, which has been shown formally. Okay? And this is at least 1,000 times or 10,000 times higher in the diffusion coefficient in the substitutional interstitial diffusion. Now, the practical applications, predepositions, we use the Henley's law, because we are not having that heavy concentration of dopants, and the partial pressure of the dopants is related to the concentration linearly with the Henley's constant. That is the Henley's law, right? Okay. And then we have a solubility limit, and before the solubility limit, the silicon atoms is going to be doped with the silicon atoms. Now, what we try to do here is that we want to solve the fixed second law to get the dopant profile along the depth here from the surface. Okay, and then we determine the junction depth For this junction depth, we want to see from the surface how the dopant concentration is going to be changed. Obviously, we have a high concentration of the dopants at the top, and then if you move along the depth of the single crystal, you have a lower diffusion concentrations, dopant concentration along the depth. So if you plot, this is the depth, and this is the surface, okay, and then at the very surface here is going to be limited by the solubility limit. Solubility limit, okay, of the dopant down to the silicon matrix. And then obviously it's going to go down as you go along the depth of the single crystal. This is a dopant atoms profile, dopant concentration. And in order to get the exact profile of this, what you have to do is you have to solve the fixed second law. And fixed second law says round T over round C, the dopant concentration change with respect to the diffusing time is going to be minus D over round x square over round square C. That is the fixed second law, simplified fixed second law, right? So we want to solve this partial differential equation, and then the solution is going to get a form like a C concentration of dopant with respect to the x and the time is blah, 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 something like this. That is the solution of this partial differential equations. And we have first differential with respect to the time, and the second derivative with respect to the x, so that we need the three boundary conditions. In order to solve this equation, we need three boundary conditions to solve this fixed second law, okay? And these three boundary conditions is different for each cases. We have the pre-deposition and the drop-in case. We have different boundary conditions for those two steps, so that we are going to have a different solution for the pre-deposition and for the drop-in process. Okay, so we have a different dopant profile depending on the process that we have. Okay, and the boundary conditions has been summarized here for the pre-deposition process. And 0T means at the surface, at all the time. The surface of the diffusing process in the silicon wafer, surface of the silicon wafer, is always maintaining the concentration as a solubility limit. Beyond the solubility limit, the dopant atoms is going to be diffused into, or it's just sitting on the surface, which is going to be removed afterwards. Okay, so the surface concentration is going to be limited as the solubility limit. That is the boundary conditions for the pre-deposition. And if we assume that infinite long depth of the single crystal silicon, that the 600 micron, the thickness, we can assume that it is infinite, because we're going to diffuse at most 1 or 2 microns at most. Typically 1,000 angstrom at the junction depth, so that comparing to that, the 600 micron, we can assume that infinity. So at the very far end of the silicon wafer, there is no dopant at all. We start out with the zero concentration of the dopant atoms. Okay, and then we do not have any initial dopant concentration of the silicon wafer, so this is the initial conditions. And 2 boundary conditions and 1 initial conditions, so that we have 3 boundary conditions. So basically, we can solve this fixed second law, and the result is a complementary error functions. Okay, that is a complementary error functions. So the dopant concentration after the pre-deposition, we end up with the complementary error functions. And during that pre-deposition process, the important thing is not the profile of the actual dopant atoms in the silicon, but the total amount of charges, total amount of dopants during the pre-deposition process. So the actual profile is important during the drop-in process, but for the pre-deposition process, the profile is not important. The amount of charges that we are going to put on the silicon wafer surface, and that is going to be integration from the surface to the infinity, and then we are going to integrate this complementary functions, and we end up with this simple equation there. Okay, so that is the amount of dopant atoms that we are going to put during the pre-deposition process. Now, this is the solubility limit has been shown here. You notice that typical dopant atoms like a phosphorus, boron, arsenic, and antimony has a high solubility limit compared to other gallium, aluminum, or gold, or things like that. Okay, and that is very important if you want to have a low resistance. Then you have to put a large number of dopant atoms, right? And the number of atoms that you can put in the silicon atoms without disturbing the single crystal nature of the silicon is the solubility limit. So you should have, your dopant should have high solubility limit in order to have a low resistance. Okay? So the typical dopants that we have has a high solubility limit, so that we can have very, very low concentrate, low resistance of the source and drains. Okay, is pre-deposition dopant profile, and that is a complementary error function. And the profile itself is not that important in most of the cases, because in the pre-deposition processes, we just put a certain amount of dopant atoms which is supposed to be diffused in during the pre-deposition driving process. Okay? And driving process, we need 3 boundary conditions, but as you can see, we have no more source of the dopant, so that